Hi everyone, Ms. Patel Dane here with topic 7.14, free energy of dissolution. This is also the end of Unit 7 for AP Chemistry. So in this lesson, you're going to learn what the solubility of a salt is with respect to enthalpy and something called entropy, and why some solutions dissolve while some solids dissolve while others do not. So as a reminder, enthalpy is delta H. When we look at the potential energy diagram, and this is from a New York State Regents, but it's pretty universal, the enthalpy is the potential energy of the products minus potential energy of the reactants. Now, in this case, so when we see the line for the products on the right-hand side, that's going to be lower than that of the reactants. So when you subtract the products minus the reactants, which of course is arrow number 4, we get a negative delta H, and that means that it's exothermic. It's going to release energy into its environment. Conversely, if your products, that line was higher than your reactants, when you subtract the potential energy of the products minus potential energy of the reactants, you see that you have an endothermic reaction or a positive value. So again, that's review from thermo. What is new here is entropy, and I use this as an example. If you ever babysat a kid and they're playing with blocks, or you're playing with blocks, and all of a sudden they come in and they tear it all apart. Well, kids are a sign of entropy. Entropy means disorder. And you might also equate this perhaps to your bedroom as well. So we use delta S, as our value for entropy. Now, a negative delta S means that it's more orderly, right? So this is when the structure was completely built and perfect. And that means, of course, less disorder. Positive delta S is what you see here. It's less orderly or more disorder. So entropy means how disorderly something is. If it's positive delta S, again, you see more disorder. Gibbs free energy, or delta G, is pretty much the energy available for a reaction to occur. So if it's a negative delta G value, that means that this reaction is spontaneous, and that means that it doesn't need an extra input of energy. Versus if it's a positive delta G, it's non-spontaneous, means it needs an input of energy. I use this battery as an example. That is an input of energy into a substance. Now, what's happening inside the battery is going to be a negative delta G. That happens spontaneously with chemical reactions. We'll go more into Gibbs free energy when it comes to Unit 9 of AP Chemistry. So when we have substances dissolving, well, you've got your solute particles, and in this case, it's an ionic substance. Let's call this lithium fluoride, right? The lithium would be the positive, the fluorine would be the negative. And then we also have that it's dissolving in water. So water would be the solvent, the lithium fluoride would be the solute. So here we see that the solvent, the water, is going to help to kind of break apart the ions away from one another, and then those water molecules will surround those ions. That's the dissolving process. So let's think about this step by step. So step 1, we need to have some sort of, we have to have the solutes themselves separate. So right now, those positive and negative ions have a great attraction to one another. We have to separate them apart from one another. Step 2 is separating your solvent molecules. Water molecules also have a great attraction towards one another. We see that with hydrogen bonding, right? And so we have to separate those out as well. And then step 3 is when your solvent surrounds your solute, and you're then you have that dissolving process that we normally see, right? So let's think about what happens with enthalpy, delta H, and entropy, delta S. So going back to step 1, the solute ions are separating. Well, again, we have a great force of attraction between the positive and the negative ions, so we have to add energy in order to overcome those forces of attraction. Right now, as is, those solute ions are very orderly, right? But we're going to see that they're going to become more disorderly when we separate them out. Remember, it's the blocks kind of going all over the floor. That's going to be a positive delta S. Step 2, your solvent molecules. Well, water molecules, again, they're very attracted to one another. So you have to add energy in order to overcome those forces of attraction. And when they become more disorderly, we see a positive delta S. Now we're seeing that we have the solute and solvent forming attractions, right? So in the case on the upper right-hand side of the picture, we see the positive ion, maybe that's lithium, being attracted to the negative end of the water molecules. So that ion dipole we see is ending up being a negative delta H value. So it's an exothermic process. In terms of entropy, we end up seeing a little bit more order forming here. So you're seeing water molecules arranging themselves pretty nice and neatly around those ions. Now, overall, when it comes to Gibbs free energy, will this reaction actually occur? Well, it depends on how much energy is actually being released from the reaction versus how much is actually being absorbed. And that's something that we'll go more into detail in Unit 9 with. So at this point, can you determine changes in enthalpy and entropy that occur in the dissolving process? Thank you for watching. Have a great day.